I always look sort of ahead and thinking about students in the future and being responsible. The reading level on this is pretty high. So I'm going to do sort of some little explanations as we go, and it's a good chance for you to sort of get some experience with some higher level reading. Okay, I got to blow this up here because my site here just isn't quite as good as it once was. No? Okay, here we go. I would suggest if you have a highlighter, use it. If you don't, little pencil or pen, underline or star or something like that. There'll be a few things that I'll be highlighting as we go here, kind of thing. Okay? And this whole idea of models and theories and stuff falls under what we call the nature of science, which is in cluster 0 of the curriculum. Starting tomorrow, vectors. Vectors. Now, does anyone know, did you guys notice that today is National Talk Like a Pirate Day?
No.
Yeah, it is. Do you know what a pirate's favorite letter is?
R.
You'd think so, but he really loves the C.
Uh-huh.
Well done. Thank you. Thank you very much. Yeah. Anyways, I try to get to vectors by International Talk Like a Pirate Day because we do a pirate treasure hunt. So unfortunately, you're not going to have that today, but I will do it for you. Don't worry, it just won't be on National Pirate Day.
Can we get high on National Day?
No, because you won't be in here. That's mine. So you need a ruler and a protractor starting tomorrow. Okay, so let's talk about this. I need you to listen now. I've kind of been filling some space here because I know that you need to finish up your conversations, but now it's time to listen. Excellent. Okay, science is more than just a collection of facts and observations. We're going to make sure I'm recording here, yes. Models, laws, theories, and evidence all play an important role in understanding the nature of science. A scientific model is a conceptual representation or idea in your head that stands for and helps explain other things. Do you think that should be highlighted? Seems like a definition, doesn't it? A scientific model is a conceptual representation that stands for and helps explain other things. A model can be a physical or real thing, like the globe up there on the shelf. It can be imagined in your brain or maybe in a drawing, like the Bohr model, or mathematical, numbers and formulas. In science, we develop models that have explanatory and predictive powers. So they explain and they predict, like the model of the universe. And we test these models in the world around us. If our model predicts our observations, we accept the model as a valid description of our world. However, if our model encounters discrepant events, and I'll explain that in a second, and fails to provide adequate explanations, we begin to modify our model or search for an entirely different model. A discrepant event, a discrepancy is an error, a mistake. So a discrepant event is something that doesn't fit the model. For example, if the model of the globe, the model of the Earth was a flat disk, one would expect that eventually you would fall off the edge. To date, there has been no reported people falling off the edge. That is a discrepant event. Hasn't happened, and so we should discard that model. However, if our model is the globe, and then suddenly people are falling off the edge of the world, literally, we need to change our model. Okay, that's what a discrepant event is. Another good example of a scientific model, a good example of a scientific model is the model of the solar system. At one time, it was thought that the sun revolved around the Earth, and this geocentric model of the universe was considered to be a true representation for many centuries. Geocentric, you might want to highlight. Okay? Everyone believed that the Earth was at the center, because when they stood out in the afternoon, where did the sun go? Across the sky. It looks like the sun is going around the Earth, doesn't it? And people tend to be very self-centered. They would just assume, oh, we're at the center. Okay? You see the stars, the moon, everything goes around the Earth. Okay? So that's called the geocentric model. The model encountered a discrepant event when the retrograde motion of the planets did not exactly fit the epicycles of the geocentric model. Oh my God, stop being here. Okay? Retrograde motion of the planets did not exactly fit the epicycles of the geocentric model. If you watch the planets, okay, the stars go across the sky, Okay? And the planets would actually go, and if you sort of imagine, I'm going to draw a picture, you imagine the path of the planet, it would have this sort of little curly thing. And it would do this retrograde motion, backup motion. You guys are not listening. So that you need to listen. You can't have side conversations with this. You can't. It's maybe not the most exciting thing to do, but you gotta listen. Retrograde motion. So these planets would actually sort of back up as they track them over many nights. In fact, the word planets comes from the Greek planetos or something like that, which means to wander. Because they would actually wander amongst the stars. There was something up with these stars. Can anyone pick out a planet on the sky? You guys know the difference between planets and stars in the sky? No. The planets tend to be brighter. Okay, they're a little bit bigger. Once you've sort of been shown them, you can go, oh yeah, okay, right. Okay, and if you watch them, they do not follow. You know how the constellations, like the Big Dipper, you know, they're usually inside by then. Okay, it kind of looks like that, right? There's all those different constellations, right? They always look the same. Well, the planets don't follow that. They sort of wander around. That's where the name comes from. So this discrepant event, the planets didn't make sense. Why would they do that sort of little curly curl, loop-de-loop? A new model, the Copernican sun-centered model, provided a simple explanation of the movement of the planets, and it predicted the phases on Venus. So Copernicus, about 1600, 1500, said, you know what? Earth not at the center, sun at the center. And when he did the math, it explained why the planets did that little curly curl kind of retrograde thing. It also predicted the phases on Venus. Now, what they mean by that is, you guys all know what the difference between a quarter moon, half moon, full moon is? Yeah. Right? Those are called the phases of the moon. Venus, which is a planet, really tiny, almost looks like a star in the sky. Copernicus said, you know what? That's going to be true for Venus as well. About 300 or 400 years later, well, maybe not that far, I guess, maybe only 100. Galileo invented the telescope, looked at Venus, and lo and behold, Copernicus was right. Evidence that predicted something that was then found to be true led more evidence or led us to believe that that model was true. Observations can be used to test models, both externally or by thought experiments, as we rethink and apply our model to new and sometimes discrepant situations. Our observations can lead us to identify regularities and patterns in nature. We call these regularities and patterns scientific laws. Laws. For example, a simple scientific law would be what goes up must come down. And as I stated Friday, if only I could use my Jedi powers and keep it up. I cannot. Anything that I throw out. We can also deduce laws given a certain set of conditions. For example, if light is a wave, we can geometrically show that the ratio of the sines of the angles of incidence and refraction is a constant. Don't need to know that. Yeah, I know, because it's not important. It's called Snell's law. It's actually in grade 11 trick that we never get to. Okay? If light is a wave, we can use rules about waves to make predictions about them. We often also represent laws as mathematical relationships, like Snell's law that I just mentioned, Ohm's law, Charles' law, Newton's laws. Usually if it has the word law in it, it's a law. Contrary to popular belief, laws are not absolute, but are often constrained to certain conditions. Ohm's law is valid only for some materials, and our pressure laws are constrained by temperature. Even Newton's laws are valid only in inertial frames of reference, and I'm not really going to get into that today. But I will say this, what goes up must come down is only true when? You're on Earth, because if you were orbiting and you threw something up, what goes up? Keeps on going. Scientific theories form explanatory systems for their phenomena and the corresponding laws, and may include presuppositions, i.e. assumptions, models, facts, and laws. For example, Einstein's theories presuppose that the speed of light is constant in all frames of reference. It assumes. In Einstein's world, Newton's laws, such as F equals ma, hold only for objects that are moving much more slowly than the speed of light. So scientific theories form explanatory systems. Fancy word for? They explain things. They explain the laws. They explain the models. Again, theories do not become laws. Kind of messed that up, didn't I? We must be very careful how we use the term theory. In everyday usage, the word theory often refers to an idea that is not proven. That's how people on the street speak, right? You guys are now smarter than that. You are not the average person on the street. You are a grade 11 physics student. It's partially true that some theories, like many cosmological theories, are speculative. That's a word that we came up with on Friday, and are based on little evidence. Additionally, children often hold simple or naive theories about why things float or why the sky is blue. Hypotheses or proposed solutions are also often speculative, and we often seek to build support for them through predictions and observations. However, other theories, like theories of radiation, metabolism, or chemical bonding, have considerable evidential supports. We can explain radiation quite easily, and the evidence is there to back it up. It's impossible to prove our theories. Okay. It's impossible to prove our theories. No. I hate working in Word. It's impossible to prove our theories. It is. Colin. No, thanks. Impossible to prove our theories for every possible case. But robust theories, there's that word there, explain a great deal, and we sometimes literally bet our lives on them. Therefore, scientific theories lie along a spectrum from speculative hypotheses to robust explanatory systems. In science education, we often use early models of theory that are adequate for a less sophisticated understanding of a scientific concept. In other words, we lie to students. You know, maybe when you first learned about adding and subtracting, and they probably said when you're subtracting, you always put the bigger number first, or the bigger number always was first, because you couldn't explain what 3 minus 7 was when you were in grade 2. And then you learned about integers, right? Same idea. And at one point, they probably told you you can't divide by 0, right? Yes, not true in the real number system. Right? So there's all these little lies all along your way, all along your student career. I'm probably lying to you right now. But there is, right? And we do that because you don't have the understanding yet to sort of, you can't handle the truth, to quote Jack Nicholson. I'd like to go back to this. Therefore, scientific theories lie along a spectrum from speculative hypotheses to robust explanatory systems. You probably have this written down already, but let's do it right here. Especially for those that weren't here the other day. Speculative and robust. Speculative and robust. Speculative theories. Is yours slightly different?
No. What is different? What could yours not? Yeah.
Oh. Well, you shouldn't follow. Okay. Thanks for finding. So, speculative theories, remember this. These are things that are little evidence, not generally accepted, still sort of in the investigative stage. Could easily be dismissed as incorrect. Robust theories, lots of evidence, generally well accepted, pretty much fact. Still just a theory. Yeah, air quotes, just a theory. Theories are good. Okay, so back to this science education, we often use early models or theories that are adequate for a less sophisticated understanding of a scientific concept. For example, Bohr's model of the atom that you guys are all familiar with, you know, the circle thing with the dots, right? Explain all the phenomena one might examine in an introductory chemistry program. More progressive theories require a more extensive background. I think they still do it. I know I taught it when I taught it in grade 12. Bohr's model is a complete fabrication. Lie. Not true. Sorry. But it works just well for introductory chemistry. Okay? Once you get into the sub-levels and stuff, and your P levels and S levels, and things overlap, and it's like, oh my God, it's hard to figure it out, right? So you'll get there. While it's important that our understanding of the nature of science is embedded in the context that the world is rational and can be understood, we never really know if we've achieved the most rational explanation. In science, truth is elusive, but our beliefs must extend far beyond individual opinions. In science, we insist on an evidential argument. You can't just say, well, I think it's this way. Have you heard of Aristotle? Probably. He had some crazy ideas. People believed him for like well over 1,000 years. And his evidence was, I'm Aristotle. That was it. People believed him for 1,000 years. More on that when we get to gravity. The theory-evidence connection. One of the main questions that scientists are concerned with is the relationship between theory and evidence. It's not unusual in science education to make a knowledge claim in the form of I know that, or something along those lines. For example, while discussing health with your doctor, she might say that lowering cholesterol level lowers one's risk of heart disease. To further the claim, support is found for that knowledge claim. We often call this support evidence. The nature of the evidence presented will depend on the background knowledge of the knowledge claimer, in this case, a doctor. For example, she might stress the statistical evidence or discuss the latest hypothesis of the underlying mechanism that relates cholesterol level and platelet formation. Of course, one might simply quote a recognized authority like the Department of Health and not attempt to formulate an argument at all. So when you go to see your doctor, they might be explaining things to you. The doctor has to sort of make a decision, a reading of the person's background. Is this person educated? Can I go into the science behind what I'm telling them? Or should I just say, stop eating eggs? Eggs are good. But you know what I mean, right? They have to speak to their audience. When you are teaching a 4-year-old, you don't use big fancy words, right? Likewise, I'm trying to explain some of the big fancy words in here to the 17-year-olds in the room, 16-year-olds. Okay? Since the background knowledge of the claimer and the intended audience may be different, an evidential argument must be given that makes sense. That's what I'm talking about, to the audience, and connects with their prior knowledge and experience. Consequently, a selection process of theory choice is involved in deciding the adequate, okay, blah, 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 blah. However, accuracy is not the only characteristic of a good theory. See where I am? However, accuracy, follow along, you guys. Colin, I need you to focus. They're all different? Okay. I'll have to make sure that I get the same one. Just, yeah. No, the only part that I'm having. I'll try to read yours, mate. Okay, you guys, seriously, you have to stop talking. It doesn't work. I know how this plays out. It plays out in, I don't understand this, Mr. Bennett. I'm going to get this wrong on the test, or I already got it wrong on the test. Here's where you got to make a decision. You can't visit physics. You can't. Stop. I understand it's hard, but you have to. I'm going to try to find it here. Oh, it might not be, yeah. Yeah, I scrolled down, yeah. Yeah. I don't know. Not sure. Okay. Please try to find this sentence, but you don't need to highlight it. Okay? Please try to find this sentence. However, accuracy is not the only characteristic of good theory. Okay? Okay, good. Follow along with me. That's what you should be doing, not talking to your neighbor. When two theories are equally accurate, the better theory is often the simpler explanation. And there's a rule for that. I'm going to explain it. It's on the third handout. I'm going to explain it a little simpler for you. Give you an example. The Copernican model of the solar system was no more accurate than the Ptolemaic model, with a series of epicycles to account for the motion of the planets. In the face of equally accurate models, Copernicus' theory simplified the model of the solar system tremendously. So Ptolemy was the guy that said, hey, Earth's at the center, and he had all these crazy diagrams, and it all was accurate, but it was really super complicated. Copernicus put the sun at the center, and all of a sudden it looked simple. Here's the sun, and everything else just kind of went like this, and everyone was like, oh yeah, that's simpler. Let's go with that one, right? There's a rule for this. I'm going to explain right away. Furthermore, a good scientific theory has explanatory powers that cover a broad scope. In other words, it explains lots of different things. It explains a lot, even phenomena it was not intended to explain. The scope of a good theory also extends to bold predictions, like those phases on Venus. Often these predictions, such as Einstein's prediction that light would bend near large bodies, are not confirmed until years later. Einstein predicted that. Many, many years later, they found that to be true. The theory explains something they hadn't even thought of yet. and they couldn't even experiment on. Okay, I'm going to stop about that. The next handout is sort of the same topics. The reading level is sort of dropped a little bit. Okay, I'm going to assign it for reading at your own time, whether that's in class or not. Okay, so you've got about a page and a quarter page and a little bit. Okay, and there are 6 questions to sort of summarize your thinking there. Okay, so I'm going to leave those for you. Not just, I'm going to do that right now. Okay, so this is on your own time, and then there might be time in class because we're going to give people time to submit to Schoology as well. Okay, let's talk about clever hands. Try to stay with me here. Here's a little break. I'm going to go on, I'm going to call it clever hands. You've got 20 seconds to talk to your neighbor. And then when I'm done, conversation ends. That's how it works. All right. So I have the story of clever hands up on the board here. This should match what you have. Yes, Colin? It's a donkey or a horse? It's a horse. Okay. So this is known as the law of parsimony. It's something I expect you to know. It's actually pretty easy. This is a really good example. Not all explanations for a knowledge claim are created equal. Some explanations involve more details and make more assumptions than others. In other words, they are complicated. Assume you were confronted by 2 explanations for the same phenomenon. Both explanations seem equally plausible. What does the word plausible mean? Possible, or it could happen, or equally likely to be true. There's a chance that it's true. Which one would you select? The one that involved numerous assumptions and details, i.e. the complicated one, or the one that involved fewer assumptions and details, the simple one? Which one would you choose? The simple one, people say. If common sense tells you to select the explanation that makes the fewest assumptions, remember assumptions also require explanations, then you already have a good understanding of the law of parsimony. So the law of parsimony, if you had to explain it right now, what would it be?
Take the easy.
Well, okay. Pick the simplest explanation. Yeah. Keep it simple. Here's an old but excellent example of the law of parsimony. This is a true story. In the early 1900s, Mr. Wilhelm von Osten, a retired mathematics teacher, owned a remarkable horse named Clever Hans. Hans became world famous because he could apparently solve problems, mathematical problems, that involved decimals, fractions, tell time, and read, among other remarkable abilities. It was a super horse. For example, someone, his trainer as well as strangers, might ask Hans what 7 divided by 4 equals. Hans would tap out the answer with his hoof and receive a treat when he was correct, which was well over 90% of the time. The horse could do math. Yeah, same thing. A committee that included the noted German psychologist Karl Stumpf was appointed by the German government to study the phenomenal horse and prove that his so-called abilities were nothing but a hoax. The committee completed their task and reported that although they were unable to prove that Hans was receiving intentional cues, they remained unconvinced that he was able to solve such mathematical problems and complete some remarkable feats by using his cognitive processes. In other words, they couldn't prove that the horse was cheating, but they still didn't believe it. Stumpf's assistant, Oskar Fuchs, decided to continue investigating the phenomenal horse. Fuchs conducted several experiments and concluded that when Hans could see the person asking the questions, he was able to supply the correct answer. So whoever was asking the question, the horse could see them, horse was right. If Hans could not see the person asking the question, then his performance fell to near zero levels. In other words, he was wrong all the time. Fuchs was faced with 2 alternative explanations for the horse's abilities. Either Hans understood the questions and was able to use cognitive processes, his brain, but only when he was able to see the questioner to solve the problems. Or the person asking the question was somehow inadvertently cueing the horse when to stop tapping at the appropriate moment. Like they were somehow saying to the horse, stop tapping, you're right. Applying the law of parsimony, which says pick the simplest explanation. So which one do you think is simplest? Either the person is accidentally telling the horse when to stop, or the horse was only smart when they could see the question.
The second one's similar.
The second one too.
You guys are a bunch of kids. Applying the law of parsimony, Fuchs chose the latter explanation and persisted in his investigations. He finally determined that almost everyone who asked questions of hands made a minute upward movement of their head when the correct answer was reached. They went, their eyebrows went up like this, and their head went up like this, and the horse went, oh, I must be right, I'm going to stop. Still a pretty smart horse. He knew that when the person did this, right, he should stop tapping and he would get an apple or a sugar cube or whatever horse like. I don't know what a horse is like. Grass. Okay? If you apply the law of parsimony as you evaluate knowledge claims, you are well on your way to becoming a good psychological skillset. Don't worry about the last part. Students do this all the time. I ask a question and they'll answer it and they'll wait for me to go like this, and then they go, right? But if I do this, then they will always do what? They always say one thing and then they don't get a response, so they automatically change their answer. They do it all the time. You watch for it, because I will refuse to give you that body language that you're right. Right? Because I want you to think. Do you notice that, Riley? I'm gonna ask Riley a question. No, I'm gonna ask someone who I don't think I know the answer. No, you might know the answer.
What's the question about?
Kat, did the Rough Riders win or did the Eskimos win yesterday?
I know.
Come on, play along. See how I did that? I went.
You feel like I'm wrong though.
Because she is wrong, right?
Well, because I'm wrong the whole time.
No, but I'm giving you an example, right, of that feedback that people, when I go like this, kids know right away, oh, I must be wrong, look at the other end, right?
Hold on, let me ask that.
But when people do that, or just me?
No, you do that.
Oh, yeah? What, are you crazy?
Yeah, it's just like,
Yeah. You won't see it from me. Yes, call.